what's going on? What have I given you all? Do you even have a homework assignment right now? I don't think so. Okay, cool. I want to fix that. Sorry, but I do. I do want to fix that. So, this one's kind of a handwritten one, and some of it will make more sense after today. I don't even know if I hit record. Is that recording? Sorry.
Yeah.
Okay, thank you. Cool. And they're kind of all over, kind of like how I'm feeling in general, just all over the place. Hello. Okay, cool. So here's some homework. These are going to be, like I said, a little bit weird. I should have probably written these up on World Class, but I didn't. Cool. So homework. Let's shoot for next Monday and see how that goes. This is all a lot of compactness stuff. So prove that if K is compact, and we're going to talk a lot more about compactness today, then the supremum of K and the infimum of K exist, and this is probably the warm-up problem for the group, are elements of K. I almost feel like it was something that you brought up as characterization of, I don't know, I remember you saying something about sup and inf being in the sets, and I can't remember what the context was, Christian, but let's prove this officially. Was it, yeah, okay, cool. And then, so that's homework number one. Number two is, which sets are compact? And then there's an A here, which is Q intersect 0, 1, and B, Z intersect -3, 4. That's an open parenthesis there. And then, so that's problem 2. Problem 3. One of these sets is compact, one of these sets isn't. I'll just kind of give you the punchline for it. For the non-compact set in number 2, find an open cover that doesn't have a finite subcover. This will be a challenging problem. This is pretty tricky, for sure. And we'll talk more about the open covers. And maybe let's just make this due on Wednesday, next Wednesday, because I feel like there's no way you're not gonna have questions. Like if you actually put some time, just put in like a little bit. You and me, we're gonna have lots of coffee, Camila. We're gonna jack up. We're gonna get like pumped. We're gonna do a few problems this weekend and maybe not solve them, but be like, huh, I spent time on that. I don't know what to do. That would be great. And then, so that's number 3. Number 4 is true or false. And for these, if true, give a brief proof. If false, give a counterexample. Maybe I just need more exercise or something. That could be it. I didn't get much. That COVID really just fucked me up. I've got all sorts of pictures drawn all over the place here. Here we go, cool. So A is arbitrary intersections of compact sets are compact. So this could be uncountable, this could be countable, certainly could be finite, but you're gonna see trouble when you go to the infinite cases. Arbitrary intersections of compact sets, which I'm gonna abbreviate CPT from now on. Right now it's costing more to explain this abbreviation, but that means compact. Of compact sets is compact. We don't know if that's true, that might be false. After we talk about one thing today, you might have a better feeling for that. If F1 contains F2, so here I've got a sequence of sets. This one's nested in this one, so they're nested, a sequence of nested sets. In fact, these are nested closed sets, because we use that F for closed set, is the intersection of F, of all the F's, is the intersection non-empty. And I got one more. This one definitely we're gonna have to get to. Construct and a generalized Cantor set. Now, we haven't talked much about the Cantor set. Does that even ring a bell when I say Cantor set? Nah. Okay, cool. So I have a generalized Cantor set where at each stage we remove the middle alpha portion of what's left. So here's how it's going to work. You're going to start with C0 is the closed interval 0 to 1. And then C1 is you're going to pull out the middle alpha section here. So if this is 0 to 1, and we're going to pull out the middle section of length alpha. So there's going to be some computation to do here. So this is 0, 1 minus middle alpha section. Alpha is a number between 0 and 1. And then you're going to have something that looks like this. So here's C1. C2 is you're going to remove the middle alpha portion from each of these. So this section here, you're going to scale it down. You're essentially removing a piece of length alpha squared from there and a piece of length alpha squared from here. So C2 equals C1 minus the 2 middle alpha sections of C1, that's a minus, and C3 is keep removing these middle pieces. Like seriously, this will make more sense once I get to the Cantor set itself, the classic Cantor set. So keep on removing pieces of C sub n, like the Cantor set. And then I have some questions on this. So that's 5. 5a is how long is the remaining, actually here, so let's C equal the intersection of all those C sub i's. Everything that happened here, it's the intersection of all of those. How long is the remaining, how long are the remaining pieces? to do that today with the Cantor Set, so you'll see what I mean by that. And I'll probably type up some stuff to make this a little more formal. B is what is the dimension of the final set C. We'll talk about that too. This is enough. That's plenty. It took me 10 freaking minutes to write it. So if I'd actually spent 10 minutes at home doing that, guess I could have done it, but then I wouldn't have been able to waste time drinking tea and watching TikTok. So I think you understand my predicament. Shit happens. Sometimes it's hard to do your job. So, but this is good. This is good. This is a nice problem set. I'll have everything back to you on Monday that I owe you. Let's get rolling. First off, let's talk a little bit more about compactness. So I think last time I defined compactness as a set is compact if it's closed and bounded. I want to kind of pull back and give a slightly different definition. Because often what happens in analysis books is that's not the definition that's given, it's a characteristic of them in the real numbers. Compact sets come in every space you can possibly imagine. So let's talk about a different way to approach compactness. So we say a set K is, and I'm going to put here sequentially compact if every sequence X of n that's contained in K, I don't know if it converges or not, it's just an infinite list of points, has a subsequence X of n sub K. Let's do J because we already got K for our set. X of n sub J that converges to some X that's actually in K. All right, go ahead and write that up and then let's just talk about it. So you can call this compact, but it's good to know that this is the sequential formulation of compactness. It's going to be equivalent to some other stuff that we already have seen. So once you get that up, what this kind of means is that, and I'll do this 2D version, for some reason these kind of still help in 1D, you've got this set K, and no matter what kind of infinite collection of points you choose from there, we can find a subset of those that converges somewhere inside here. So they converge to some point K, and that K isn't on the boundary of this set, it's literally in the set. Sorry, they converge to some X right here. So any collection of infinite points, no matter how spread out they are, has a subsequence that somehow converges to something in this set. Now the rest of the points we don't know, they're just still floating around, but there's this sub-list that settles down inside there. So let's look at just a theorem that I'm not going to prove all of, but I'm going to prove some of it. The following are equivalent. Part one is that a set K is sequentially compact. Two is the thing that I gave you as the characterization. So this characterization was K is closed and bounded. that 1 and 2 are equivalent, so let's just put a little note here. The equivalence of 1 and 2 is sometimes called the Heine-Borel theorem. Heine-Borel theorem is really nice because it takes this kind of very hard to think about characterization. Oh shit, I got to think about every sequence and every subsequence, and does it converge inside there? And you can take that problem and turn it into something a little chiller. Is it closed? And closed means that it has its boundaries, there's no like weird soft open parts. And is it bounded? And that's an easy thing to always see. Bounded. Does it live in some just disk? Can I see the edges of it? Or is it unbounded? So this is called the Heine-Borel theorem. And then 3 was this other characterization I gave you that was super weird, is that every open cover of K has a finite subcover of K. So that no matter how you cover this set with this set K with open sets, for us, think open intervals, you can always pull a finite selection of those and still have the thing covered. So let's talk for a minute about all this stuff. We'll look at some examples. Let's actually do the proof. 1 implies 2, so that you can see how this works. The open cover stuff is pretty intense. I don't know that it's worth our time to think about it. It's really weird and non-intuitive. But let's just do a chill proof of a few things. So first off is that number 2 implies number 1. This is chill. This we got. Now we're going to work through this because I want your help on this. So we're assuming that we have a set K, it's closed and bounded. So assume K is closed and bounded, and that X sub n is a sequence in K. Alright, so I got a sequence in K. K is closed and bounded. How can we, so first off, what we need to show is there exists a subsequence that converges to some X in K. What are some major results? So we've got a sequence. We know 2 things. It lives 1 in a bounded set, and 2, it lives in a closed set. So let's think about each piece separately. What does having a sequence in a bounded set get you? Think major theorem.
Sequences are bounded?
Yeah, what result is that? You're right.
Like the name?
Yeah, what's the theorem? There's a big theorem.
That's the, is it the Bolzano-Weierstrass?
Bolzano-Weierstrass. Exactly, so perfect, nice. So since K is bounded, every sequence has a convergent subsequence. The sequence X sub n has a convergent subsequence because every bounded subsequence has a convergent subsequence inside of it. So that is by, as Christian gave us, Bolzano-Weierstrass. Nice, very good. So that just gives us the convergence sequence. How do I know that limit? So this thing, i.e. x sub n sub j converges to some x. How do I know that x has to be in the set? Think about what haven't we used? What does that mean? So what do we use? So we use bounded, right? We got bounded, got us the sequence that has a subsequence that converges, or got us the subsequence that converges. How can I use the closed? Corbin?
Any subsequence that converges to x implies that x is also in the set.
That's part of the definition of closed. So closed, since K is closed, every sequence that converges, that lives inside K, its limit is also in K. We'll talk, I'll say that in a different way here in a minute, because I've seen some faces that make me think maybe we don't all necessarily remember this or believe it. And since K is closed, X is in K. And that's basically the whole proof. So recall that a set F is closed if it contains all its, I'm going to say this in a slightly different way, its limit points, i.e. every sequence in F that converges to a point in F. Now I'm feeling like we should look at some examples and counterexamples before we think about the other direction. Let's just do a little bit more recall here. Got that half open interval. What's a sequence that's in here that doesn't converge in here? It does converge, but it doesn't converge in here. Can somebody give me an x of n where all these guys live in there, but the limit isn't in there?
N over n plus 1.
Oh, that's cool. Yeah. Where's that limit go?
To 1.
To 1. So check it out. This limit goes to 1. So this x of n converges to 1, convergent sequence, but it's not in there, right? So here's 1/2 is your first value, 2/3 is your next. And you see that they're moving that way, but that point's not in there. But 1 is not an element of the set. So that means this set is not open, or excuse me, not closed, because it doesn't contain all its limit points. Limit points are just places where things can pile up. So, what about this? This set here is the classic closed set. We've added in that 1, that's the trouble spot up here. So this set is closed. It's also bounded. So it's actually compact. Compact's just nice. It's got all its boundary points. It's graspable in its boundedness. What about this set here? Let's see, so 0, 1, 2, 3. That set right there, just those 4 points. Is that closed? Let me write it a different way so you can think about it. So we've got this set here, we'll call it A. And A is just the points 0, 1, 2, 3. Is that set closed? Why do you say that, Cormac? I agree.
Because its complement is open.
Yeah, yeah, awesome. So that's a great way to see it. Remember, a set is closed if its complement is open. So this set is closed because a complement, what is it? It's everything except these points. So it's negative infinity to 0. Skip 0, go to 1. Skip 1, go to 2. Skip 2, go to 3. And then on the other side, just 3 to infinity. All of these are open intervals. So a complement is open. So A is closed. Nice. Let's think about limit points. What do sequences in this set look like? What do they look like?
Just be the points.
Yeah, so it's just you've got 4 options for the things in your sequence. So your sequence has to be just one of these 4 values here. So sequences are essentially just gather these values here. What does a convergent sequence in here look like? So if I say, here's this set, what does a convergent sequence look like in here? How would you characterize it? So here's an example of one that's not a sequence that goes 0, 1, 2, 3, 0, 1, 2, 3. That doesn't settle down. What does it mean to settle down here?
Past a certain point, like it would just close in on like one of those numbers, so that like the limit would exist. So you could go into like the limit definition and just say like, because there's only 4 numbers, you would just kind of like have to choose one of those numbers at some point, so that from that point on, it's just that number.
Yeah, 100%. And eventually it's constant. Eventually, any convergent sequence here is eventually one of these 4 numbers. Any convergent sequence here is eventually constant. And it's going to equal 0, 1, 2, or 3. Which means, of course, it's going to converge in here because it's literally just grabbing the points from here. It's not like you can get close to one of these and still be in the set. You're just literally in the set all the time. So you've got some sequence that goes 0, 1, and then it's 3 forevermore. That converges, and it converges in the set. So this set is also closed for that way as well, that it contains all its limit points. But I like this way is sweet. It's for some reason a lot easier to think about. Is that set compact? Yeah, why do you say that, Cormac?
It's also bounded.
It's also bounded. So it's closed and it's bounded. Bounded by whatever little interval you want to bound it by. So this set is closed, bounded, so it's compact by the Heine-Borel theorem. Closed and bounded implies compact. Just practicing using those definitions, thinking about them, especially compactness. Okay, so now we need to show that closed and bounded implies sequentially compact. Now we're going to show here. Now we're going to show that 2 implies 1.
Didn't we just do 2 implies?
Oh, did we do 2 implies 1?
Yeah.
Yes, thank you. Thank you. Yes, thank you. Good call. I don't want to do it again. Good. Appreciate you. So now we're going to do 1 implies 2. That sequential compactness, i.e. show sequential compactness implies closed and bounded. So can you just take a minute and show the closed part. Take a minute and just try to pull these bits together. So first, we show, and let's say that K is closed, assuming the sequential compactness. So that means you have to take a sequence that converges in the set and show that the limit is also in the set. Or a sequence from the set that converges, show the limit point has to be in the set. Making any progress? Kind of. Gosh, it's all right. No, it's definitely not you. It's me. So, why does the convergence of a subsequence give you that the original converges? I feel like it's almost there, but the wording is, right, you got the subsequence that converges.
The Bolzano?
No.
Okay.
It's a little more basic than that. Think back to subsequences and convergent sequences. Feeling okay about it?
That's all aggressive. Is that direction?
So sequential compact means that every sequence has a subsequence that converges in the space. So be careful. It's a little bit different than that. It's close, kind of. You see what I'm saying?
Yeah.
Okay. Let's see. You're not sure? Okay. Yeah. Let's see. I'm sorry. Do you mind if I? Yeah, this is like my old man eyes, and it's so pretty, the purple. So there exists sequence. Okay, so you're assuming you have a limit of what you're trying to show. Yeah, I think so, but you still need to, yeah, I think that's the right direction. And then come back to, because sequential compactness says that if you have a sequence, there's a convergent subsequence. So you'll need to kind of bring it back to that subsequence converging in there, but you're so close. I think that's about it. How we doing? Okay. Yes, that's exactly
this
right.
compactness
Okay.
definition. So
Yeah.
I'm trying to figure out how like the sequential compactness impacts.
Gotcha. So,
So like I have to construct this subsequence show
Yeah.
that all of the subsequences converge, that converge to X, have an X in
you kind yeah, that's kind of right there. It's kind of right there, even though I know you don't have it like solid.
Yeah.
So we want to show it's closed. So we're going to take a sequence that converges. We want to argue then that the limit is actually in the set. So start off by saying I've got this X sub n in the set and it converges to some point X. I know that the set itself is sequentially compact. So I've already got this sequence. Now I
it
can,
has like a
yes,
limit, and
yes.
because it's compact.
Because it's sequentially compact,
Yes.
there's a subsequence in that sequence that we picked that converges to a point in the set.
Right.
So think about, what do you know about, if you have a sequence that converges, what can you say about every subsequence that's in there?
Also converge
To
to
the
the same.
Yes, exactly. So that's all the pieces right there, honestly.
Okay.
Yeah. Let me start writing it up here. See if that's making sense. Kind of walking through. I wanted to give Camille this minute to kind of pull our chat together. So I take a sequence in K and assume it converges. I need to show that the place it converges is also in that set to show closeness. So everybody cool on that, I think. Since K is sequentially compact, there's a subsequence of this sequence that converges to some point that is in K. That's what sequential compactness means. That no matter what list of points you got, there's a subsequence of it that converges in the set. So we've got a very strong thing here. We've got this sequence, x sub n's, that are converging to some point x. We know that any subsequence of this set converges to a point in the set. And so since that, it's almost like saying the same things like kind of over and over again. Since the subsequence of x sub n is a subsequence of a convergent sequence, it goes to the same place. If you know that you have a sequence converging to x, every subsequence of that sequence converges to x as well. And that gives us that, therefore, this limit must be in there by sequential compactness, but this limit is exactly the same as our original sequence limit. So just a quick, what did I do? I took a sequence that converged. I grabbed a subsequence of it and said, oh, this subsequence converges in the space. But wait, this subsequence goes to the same place as the original sequence, so its limit must also be in the space. It's kind of subtle. Christian, I don't know if you believe me or not.
There's two spots that I kind of
Let's talk
up on. So the first one that's more simple. It's like, how can you just assume that based off of like the definition of sequential compactness, that the set or sequence x of n that is part of K converges to x? Because like by sequential compactness, wouldn't it just be like there exists a subsequence of x of n that converges to x?
Yes, definitely. So I think it's because of what's assumed here is so strong that it's feeling like I'm assuming too much. So let's talk again. So what is the definition of sequential compactness? What does that mean?
That for every sequence x of n in K, or like within K, has there exists a subsequence x of n sub j that converges to some x in K.
Cool, awesome. So you agree with that? We agree with that. So now I want to show that the K, this implies closeness. To show closeness, I take an arbitrary sequence that does converge. So I'm starting with, to show K is closed, I take a sequence of points, these all live in K, and assume they converge to something. I have to now argue that that something is also in K, because I don't know that.
I guess like I just get hung up on like how you're able to make like that first step of assuming that like x of n converges to x. Like we couldn't, because you could have like a sequence with like that doesn't converge, I guess.
Absolutely.
That has like subsequences that converge to different points.
I think I see your problem.
Like I guess I don't really understand how you could just like assume that without like cutting out like that issue of like non-convergence in like the first sequence. If it's like with sequential compactness, you only get like a there exists for the subsequence.
True, yes.
So that's kind of where I got hung up on like trying to reconcile like the modifiers for.
So let's go back to the definition. I think this might help. And let's just really look at this definition. So K is closed if every sequence of points in K that converges to some point X gives us that X is also in K. Does that make sense? Mm-hmm. So if I want to show closeness, which is what we do want to show, right? I have to assume I have a convergent sequence to begin with.
I get like that's kind of where I get hung up though. Yeah. It's like, it feels like you're assuming like the result.
But I'm not assuming the limit is in. So that the thing that's not The only thing sequential compactness is getting us is that limit actually is in the set itself.
Okay.
So for example, let's take a look at this set, 0 to 1. Yeah? So if I say x of n is 1 over n, that converges to 0.
Okay.
0 is not in that set. But that makes sense because this set isn't compact anyway. It's definitely not closed and bounded. If it was closed, it would look like this, and I'd have that 0 in there.
Okay.
So what we're doing here is we're first taking, I don't know exactly what this set looks like. I just know that it's got sequential compactness, so that no matter what kind of sequence I take in here, there's some subsequence of that sequence that converges in here. And I don't know what that subsequence is, but no matter what infinite list of points I get, somehow part of them are bunching up in the set itself. So when we assume this compactness, we're kind of assuming that the 0 is included, but we have to get there through argument. We can't just, I don't know if this is helping or not.
A little bit, yeah. I feel like I don't know, I'm
It's subtle.
like missing something on just like, I guess like, so
Yeah.
the sequential compactness, does that imply that sequences of like a set K converge?
No.
So that's where I get hung up.
Yes.
It's like if you can't assume that like they converge, how can you assume that like all of their subsequences of those sets like would converge to the same
Yes,
place?
but that's because we're making this bigger assumption. So look where we're going here. Let me make a different diagram here. So I've got this thing, I want to show K closed. This is kind of what I want to show, right? And what I know is that K is sequentially compact. So this means that no matter what my list of points is, there's some sub-list of it that converges in the set K.
Okay.
To show this, so think about what do I need to show this? So first off is I need to take a sequence in K that already converges. But I don't know if it converges in K.
Or if K is closed, wouldn't you know that it converges in K?
But that's what I'm trying to show.
Okay.
That's what I'm trying to show. You're right, I would.
Okay, I see.
You see what I'm saying?
I do.
So for this, I'm going to take this in. I need to show that the limit of the x sub n is actually in K. And I don't know that just by taking this sequence that converges, because I don't know that this thing's closed yet. This is all I know. This is my prior knowledge. And I'm trying to show that it implies that knowledge over there. So over here, I take some x sub n because I know that I want to get to this. So I take an x sub n in K and I assume it converges. But that's it. So now I've got the precursor. If I can show that it converges to something in K, then I know K is closed.
Okay.
Yeah. So I assume it converges. Now, this is a heavy assumption, but it also tells me that every subsequence, x sub n sub j, also converges to the same place. And because I'm sequentially compact, every sequence has a subsequence that converges in the set. So x sub n converges, but by sequential compactness, there exists a subsequence, x sub n sub j, of this sequence that converges in K. Let's say it converges to a point X. And that point is definitely in there. Now, because I took a very special sequence that already converged, and this subsequence converges to X, I know that the whole sequence must converge to X. Because if you got a convergent sequence and the subsequence goes to 5, then the whole dang thing goes to 5, no matter what. So this gets me immediately because the X sub n converges. So I'm using that heavy assumption, then X sub n must converge to the same place as the subsequence does. But I got that the subsequence limit was in K by sequential compactness. So that gets the limit into the set.
I see where you're coming from.
You see?
Yeah. I guess like the last thing would
Yeah,
just be,
yeah.
So then sequential compactness, does that mean that like sequences in like the set need to be convergent? Like would they?
No. So for example, here's 0 to 1, right? 0 to 1. I'm gonna pick a sequence in here that goes X sub n is a quarter when n is even, and it's equal to 3/4 when n is odd. There's a sequence that lives in here, right? Just bounces back and forth. Does that converge?
No.
No. Does it have a subsequence that converges?
Yes.
2 of them, in fact, right?
Yeah.
And they both converge into space. So sequential compactness says that.
Okay.
You get it?
Yeah, I see where you're coming from.
But if I had done this, let's say I had done this, well, if I'd taken out one of these points, then I would have, like, let's say here, we're 0 when n is even. Well, that's actually not even in the set, so it doesn't, yeah.
But if you had like something that was like going towards 0, like 1 over n.
Yes.
Okay.
Yeah. Sequential compactness just means that some part of every sequence converges into space.
That makes sense.
You buying it?
Yeah.
Okay, that's cool. I like that you didn't buy it. No, that's great. Anybody else? Everybody else good up here? All right, nice. Thanks. That was fun. It's nice to have a conversation about stuff. Let's do bounded now. So this is a little weird, and I want to talk about it because there's a cool proof technique. So lastly, we need to show, so we just showed sequential compactness implied closedness. We need to show that sequential compactness implies boundedness. But we're going to approach on the contrapositive because we love practicing writing contrapositives in our class. What is the contrapositive of that statement? We will prove contrapositive. What is the contrapositive? Somebody help me out here. What's the contrapositive of this implication? How do we build contrapositives? Our weekly review? Yes, Camila.
Not bounded implies not sequential.
Beautiful. Right, just that construction there. We not the hypothesis and have that imply the, not the conclusion implies not the hypothesis. So just like Camila said, i.e. we're going to show that if K is not bounded, then it is not sequentially compact. And our plan's going to be this. we're gonna use the fact that K is not bounded to build a sequence in K that doesn't have a convergent subsequence. So let's write that out. Plan. Construct a sequence x of n subset of K that has no convergent subsequence. What does Bolzano-Weierstrass theorem say? What's the Bolzano-Weierstrass theorem say?
Bounded sequence has a convergent subsequence.
Yeah, so Bolzano-Weierstrass says that if I have a sequence that's bounded, there's always a convergent subsequence. So that must mean in order to build a sequence that has no convergent subsequence, I have to have not boundedness. It has to be unbounded. Otherwise, Bolzano-Weierstrass would give us that convergent sequence. So we're going to exploit the boundedness. So since K is not bounded, I can find arbitrarily large x values inside there. We can find x values, x of n values in K that grow unboundedly. And that's kind of the secret here. So in other words, for each n, choose some x sub n in K such that its magnitude, x sub n, is bigger than n. So we'll write that out, and then let's talk about what we're saying here. So you might want to make a little note. What we're going to do, we're going to choose x of 1 so that its magnitude is bigger than 1 unit. There has to be an x1, otherwise this thing must be bounded above by 1. But since I know I can grow bigger than 1, that's all good. And I also know I can grow bigger than 2, because if I can't, this thing was bounded. And then we just keep going. So we pick an x3 such that x3 is bigger than 3 in magnitude, on down the way. You know, so that eventually x sub 1000 is bigger than 1000 in magnitude. And there's just eventually something bigger than 1 billion and 1 trillion, blah, blah, blah. So this sequence has no convergent subsequence. The sequence itself flies off to infinity, either oscillating or in one direction to plus or minus infinity. But notice here that we can say that any subsequence x sub n sub j has the property that x sub n sub j, its magnitude is bigger than its n sub j. I built it like that. They just keep growing, i.e. any subsequence is also unbounded and cannot converge. Therefore, no subsequence can converge. So we built a sequence that had no convergent subsequences. That means that the K cannot be sequentially compact. This implies K is not sequentially compact. We just needed one that blew the sequential compactness. So for you, the key things to remember about compactness are this 1 implies 2. So essentially you need to remember, and let's remember this is Heine Burrell, that K is compact if and only if K is closed and bounded. And here we're going to put K as the sequential compactness. We'll just use that as our definition. Any closed and bounded set is compact. Any closed and bounded set is sequentially compact. All right. So I want to say one more property about this, and then I kind of want to shoot. Yeah, I'm just going to get into Cantor Set because I want to touch on this today. Is it okay if I erase over here? Everybody good? Okay. So let's talk about a really cool compact set. In fact, just an amazing set in general. It's kind of like the first fractal that was ever created. So let's talk about the Cantor Set. And it's a great place to go for weird examples. Pathologies, sometimes we call them in math. It's a pathological example. So the Cantor Set. So we construct it. So I start with C0 is the closed interval 0 to 1. I'm going to draw that right here. So there's 0 to 1. For C1, really this is initializing the process. C1 is we're going to remove the middle third. So equals C0 minus the middle third, which means C1 looks like this. It's 0 to 1. And then we're going to 0 to 1/3, union 2/3, and say minus the open middle third, so that you see that I'm leaving those endpoints there to 1. So it's this set here that goes 0 to 1/3, and then you skip that middle third, pick it up at 2/3 to 1. So this is C1 right here. And the game is, at every step, I'm going to remove the middle third of everything that is left. So C2 equals C1 minus, and let's just put what the middle bits is. Here we're going to remove, so that's minus 1/9, 2/9, and also remove, let's see, that's 5/9 and 8/9. Wait, is that right? Yeah, wait, that's 4/3. That's 6/9. Sorry, that's 7/9. Excuse me, 7/9. So in other words, removing these middle thirds right here. Again. So this one's gonna look like this. C2 is 0 to 1/9. Skip that middle third, pick it up at 2/9 to 1/3. That's 3/9. And then there's a bigger gap here because we pulled out, this was a 1/9, this is a third. And so then we pull out, what do we got? We got 2/3 to 4, it's 7/9, and then skip 7/9, or 8/9 to 1. So here we're removing 2 middle 1/9 length segments. And then we keep going. So the next one, C3, is I'm going to pull out, how many pieces am I going to pull out of C3? And what is their width? I got 4. I'm going to pull out 1, 2, 3, 4 thirds. And each of those is a third of the existing length, so 1/27. See that? This is 1/9. I'm gonna pull out a middle third. So I'm pulling out that little third. The width of that little bit is 1/27. So C3, we'll just do this, is C2 minus the 4 open middle 1/27th length segments. And keep on going forever. Never stop doing this. The Cantor set is the intersection of all of these things. The Cantor set is what's left over after I do this forever and ever and ever. So let's figure out some things here. Let's just do some simple math. How much was removed in total? How could we figure that out? What's that computation gonna look like? So what was the first thing I removed? Third. So removed 1/3. Then how much? 2/9, right? The 2 middle ninths. Plus 2 times 1/9. Then what did I remove? 4 1/27ths. What's gonna be the next one? So at this point, here's the stage we're talking about right now. I'm gonna remove the middle piece of everything that's left. How many pieces will I now have to remove for this one? You see 8? 1, 2, 3, 4, 5, 6, 7, 8. Every time the number of pieces I have to pull out doubles. So for the next one, I've got 8, and how wide is each one of those? 1/81. It's 1/3 of the previous cut size. And so we keep on going. So if we could get this sum, we could figure out how much we removed in total. So let's actually rewrite this. This is 1/3 plus 2/9 plus 2 squared. How about if I write it like this? That's 3 squared, it's 3 cubed, plus 2 squared, 2 cubed for the 8, times 3 to the 4th for, yeah, that's the 8, and then there's the 81, blah, blah, blah. What kind of a series is that? It is not a p-series. So a p-series has like 1/1 to the p, 1/2 to the p. Here the exponents are moving, right? What kind of series has moving exponents? Geometric. Oh, we only know 2 kinds, right? We got p-series and geometric. So this is a geometric series. What is the common ratio between terms? What do you multiply by to get from one term to the next? 2/3. 2/3. Okay. Multiply the top by 2, multiply the bottom by 3. Does this series converge? Yeah. How come, Camila? You're right. Because the r is less than 1. So it converges because the magnitude of r is less than 1. Awesome. What does it converge to? What's that formula? Let me help refresh your memory, because you could look it up, but I could look it up for you in my brain. First over 1 minus r. So first term divided by 1 minus the common ratio. What is this series? Can you do me a favor? What is the sum of this series? What's that?
Is it 1?
It is 1. First term is a third over 1 minus the common ratio of 2/3. That's 1/3 over 1/3. That is 1. How much of the original, remember the original segment was this, 0 to 1, how much of it did we remove? All of it. So we removed the entire lake. There's like nothing left, but there is something left. There is something left in these intersections. And to see that there is something left, we kind of need this result that I skipped proving, but I'm going to give it to you right now. You've got a slightly different version, but the intersection, there is something here. In fact, there's a lot of things in there, and this is going to be part of like, I just got to get to this today. There is something, see, we have the nested compact interval property. That says the following: if K sub n is a sequence of nested compact sets in other words, K1 contains K2, K3 is a subset of that, K4, bless you. Then the intersection is non-empty. There's something in there. Think about how we built the Cantor set. At every stage of the game, it was a subset of 0 to 1. So everything's bounded. All our sets are bounded. Every C sub k is bounded, and they're also closed. They're the union of a finite number of closed intervals. You can just look at them and see they're closed. We pulled open stuff out to make them. Bounded and closed, so it's compact. So C sub k is compact, therefore this is compact. The Cantor set itself is compact, and this is not empty. But there's nothing of substance in there. So let's do one last thing. I got 1 minute left. I want to show you how we can figure out how much is in there. Sorry, I'm erasing this compact property. Hopefully, I'll put it back up for you someplace here. Think about how we made the Cantor set. At every stage, like if you want to get to somewhere in the Cantor set, you either have to choose to go to the left or right half at every stage. So let's say I'm traveling through the Cantor set. Here's C0, here's C1. Let's say that if I go to the left half, I use a 0. If I go to the right half, I use a 1 to encode my journey. I'm going to encode my journey through the Cantor set. Now this one's got, each of these has a left and a right half. If I go to the left half, I'll put another 0 down. If I go to the right half, I'll put a 1. 0, 1. So I'm going to start recording this. 0 point. Let's say I go left. And then I go right. And then here I'm going to have to choose left or right again. So let's say I go right. And then I go left, 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 right, 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 left, blah, 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 blah. So this is a binary number. It's just ones and zeros. Think of this as base 2. Base 2 binary fraction. Every single one of these, no matter what you put here, that's a path through the Cantor set. So every string of zeros and ones represents a place that you can get to in the Cantor set. This is just a binary fraction. So this is a number between 0 and 1. And in fact, it's probably the number you get to, but it's a number between 0 and 1. There are as many points in the Cantor set as there are points between 0 and 1. Every single number here can be written in binary and represents a path through the Cantor set. So every single real number between 0 and 1 represents a point in the Cantor set. But there's nothing in the Cantor set, as we saw, right? It's just dust. So I just want to put this up here, and we'll come back to this. The Cantor set is uncountable. There are as many, and it's the same size as the real numbers. Same size as the closed interval 0 to 1, same size as the real numbers. We can make that argument pretty easily, but has size 0. And so sometimes what's left in there is called Cantor dust. It seems crazy that there's that much stuff left, because when you look at the Cantor set, and I'll try to find some visual representations of it, it's just a bunch of dust here, like literally, just like almost nothing. But there's a lot. There's actually more points in the Cantor set than there are rational numbers between 0 and 1, because that's a countable number. So that's all I got for you today. Thanks, friends. I'm gonna write up some better instructions for your homework, because what I want you to do for your Cantor set is I want you to build a Cantor set where we remove an arbitrary middle piece. That's your Cantor set. Instead of a third, we're just gonna use alpha as the bit we remove, and like kind of go through all this again. That's a super fun exercise. Highly recommended.